Hello, welcome back to software engineering. Today is our final lecture on requirements and our final assignment pertaining to requirements, which is going to be due on Wednesday. So we'll have wrapped up the requirements by then, and then we'll be moving on to the next phase. So be ready to part ways with requirements for at least a while. However, they will still be an important part of your life for weeks to come. All right. Let's review some more stuff about requirements. We actually have a lot to cover today, so it'll be a bit longer than most of the other lectures, which is why for finishing up the document, you also get half of class on Wednesday. There will be no lecture at the beginning of class Thursday. You'll get that entire time up to 4:15 on Wednesday as well. All right, so we've talked a lot about requirements. I think we understand the process of requirement specification, writing these things down, generating a requirements document, writing detailed and technical information about what it is that we plan to deliver. This generally serves as a contract between you and the customer. I think we've gotten that down pretty much. So let's look at some ways that we might write them, because we've already been writing them, but let's look at some approaches that we might take. Well, we might use natural language. We might use a structured language. We might use design description languages, graphical notations, and math specifications. So depending on what your project is like, you might use one or all of these. You might write your user requirements in natural languages with numbered sentences. Most people did something like this. Each sentence should express one requirement. This is a place where a lot of people made a mistake. They tried to do compound sentences or combine requirements into a single line. Try to avoid doing that. One line, one bullet, one sentence, one requirement. We'll talk some more about the other options later, but just keep in mind that graphical and mathematical specifications definitely have a place in your requirements document if appropriate, and especially those graphical ones. We're definitely going to use those in our requirements documents. You're going to have to generate 5 figures before the finale is turned in next class. So in principle, requirements should say what the system should do, and then later we're going to create a design document that describes how it's done. So that's not our task at this phase, but we are going to get to design soon. And in practice, these tasks often run concurrently because the architecture of the system critically depends on the requirements and vice versa. So these are things that are going to happen together generally. Well, we're splitting them out because we don't have that kind of organization here, obviously. We only have a few people per group, and I don't want to get you confused. But just bear in mind that oftentimes generating the design document that we're going to do next and the requirements document, those are probably going to run at least partly concurrently, and possibly even the same people making both of those at the same time. So natural language you already know. This is one way of writing requirements. Write them in natural language sentences, and then supplement that with graphical work, usually diagrams and tables. This is where a lot of people have been light so far. They've just structured it sentences. Figures and sketches are a very helpful part of requirements documentation. So this is used for writing requirements documents because it's easy, it's expressive, it's intuitive, and it's universal. Of course, that comes with a lot of downsides we'll go over in a sec. If you're going to do it in natural language, you should come up with some kind of format. You should write all your requirements in that format. You should be consistent in the way you use your language. If a requirement is mandatory, for example, you can use legalese. If the word shall appears, then it's mandatory. Will is like light shall. So the program will do this. Doesn't mean that it's mandatory. It means that it really should. Should is like an even lighter version of will. So a little bit of legalese for you today. Shall is the most binding of the legalese. Words that are kind of synonyms to will but actually aren't quite in situations where more specific uses of those words are required. Shall is the most tightly binding of the common synonyms for will. But anyway, come up with a format, use it. Use different kind of text highlighting, italics we use for non-functionals, whatever. Or highlight parts of the document that are more important. Always avoid jargon when you're writing in natural language. And try to rationalize why your requirements are necessary. I haven't seen too much of this. We haven't talked about it much, but sometimes you want to have a separate line for each requirement rationalizing why the system needs it. And of course, problems with natural language, difficult to be precise. It's difficult to be very specific when you're writing in natural language. You get closer to legalese, and legalese isn't very natural. Even like including shall already damages your clarity, so you have to trade off between naturalness and clearness. You tend to mix up your functional and non-functional requirements. A lot of you have run into that problem. We had this kind of template where you put the non-functionals in italics, but some of you are still flip-flopping on whether or not something's functional or not, and that's fine. Sometimes it's very hard to figure out the difference. And then sometimes requirements end up amalgamated together. That's bad. So like that's another pitfall that many of you have run into. You've got a bunch of your requirements grouped in the same bullet or phrase, or maybe even just a simple expression that actually should have been broken up into multiple longer expressions. Requirements tend to get clumped together when we refer to them in simple natural language. So going back to our insulin pump example from earlier, the system shall measure the blood sugar and deliver insulin if required, and then they offered an explanation for why. So in parentheses, they decided in this format, it'd be in parentheses and italics, and then it would say why it is that the system does it every 10 minutes. The system shall run a self-test routine every minute with the conditions described in the blah, 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 table 1. So they've referred to a figure that makes it much easier to understand than if you had done, say, another bulleted list here, and then again a rationalization for it. All right, so rather than natural language, you could write in structured language. In this case, you don't have any freedom to write the requirements in your usual natural way, so you come up with a very rigid and structured system to do it. This is probably not appropriate for most of your projects. It's mainly used for very specific mathematical and technical systems. Usually you'll have some sort of form you need to fill out. Might have boxes like this. You describe the entity, describe the inputs and outputs, describe the outputs and where they need to go. And you would write all your requirements in this sort of form. Obviously not every requirement fits very well into a form like this, so a lot of it is trying to put a square peg into a round hole. But for the insulin pump, it's possible. Function, compute insulin dose, save sugar level, description, computes the dose of insulin. What does it get as inputs? The sugar reading in the previous 2 readings. The source from a sensor. Outputs, the dose to be delivered. Destination, primary control loop. So obviously much more technical than the natural language version we saw earlier, but also much more specific, which can be a good thing. We'll skip over this. We already saw a good one. Or we could do a tabular specification. Sometimes we switch from the natural to a tabular because tabular is more appropriate. Tabular, of course, meaning in a table. So often we supplement our natural language descriptions. Once they get to the point where it's tough to make them in natural language, we make them in table form. So this is pretty useful when you have to define a number of possible alternatives for one action. Each alternative becomes a line in the table. So looking at an example with the insulin pump, obviously depending on the sugar level that it reads, a lot of different things are supposed to happen. So we might put those in table form instead of making a bunch of bullet points or describing them in language. It's much easier to understand. Is the sugar level falling, stable, increasing, decreasing, etc., etc.? There's at least 4 options to be had here. They all have different corresponding actions necessarily, so an easy way to specify lots of different conditions with their corresponding actions without going into confusing lingo. So consider using tables. Some of yours are definitely very conducive to tables. Especially things like turn-based games and that sort of thing can be easily structured in like a table or a state diagram. Use cases are one kind of UML diagram that we're going to look at later. I'm not going to tell you what UML stands for yet. I'll let you guess. UML is generally never referred to outside of its acronym. I will tell you at some point, but just guess for fun. Use cases just define the actors that are in your interaction with the system and then what those actors do. So these are very simple diagrams. And then sometimes after we've made our use case diagram, I'll show you an example on the next slide, we follow up with a sequence diagram to add more detail to a specific use case. So you're going to make 4 UML style diagrams today and then an additional couple. So you could make use cases as your diagrams and you can make sequence diagrams to follow it up. So let's look at some simple use case diagrams. Here you got your stick figure people. This is the industry standard, the stick figure person in the T-pose. And no, I'm not kidding. Every time you see a UML diagram, it's the stick figure dude in a T-pose. I have no idea why we all decided as an industry that that's what we were going to use, but that's what we've gone with. Then we define the actor by labeling them, obviously, so medical receptionist, nurse, whatever. And then we've got lines to some bubbles about what that particular person can do. Sometimes we connect those bubbles to other people when there are interactions between users. Sometimes it's just one stick figure and a bunch of bubbles coming out of them with different actions that they can do. It depends, but they're usually not more complicated than this. And if we have more than a handful of bubbles, we'll probably just make another diagram rather than just jamming like 20, 30 bubbles into the same one. Although obviously that varies by organization. But something like view record or edit record, we would probably have a corresponding sequence diagram to describe that in more detail. So these use case diagrams are very helpful because you can define all the different stakeholders in your systems as these little stick figure dudes, and then outline all the possible actions that your stakeholders might have with the system. So end users are going to be the biggest represented category here, but there are also probably stakeholders like administrators. In this case, there's a manager person who has to do a couple of administrative tasks. The manager is also an end user by the technical definition, but he's not using the regular version. He has kind of an administrative version that has some slightly different requirements, obviously, and a different user interface and all that stuff. So not every stakeholder is probably going to be represented because they're not all going to have direct interactions with your system. But that's one nice way to think about it. Just make a little stick dude for every stakeholder you thought of and see what kind of actions they would partake in. We know what the software requirements document is already. It's that official statement of what's going to be required of us as developers. Again, highlighting that this is not the design document. We are just trying to say what the systems should do. It is up to the design process later on, or sometimes concurrently, to describe how it should do it. So that explains a little bit of why they might run concurrently. As we come up with what we do, it makes sense to also come up with how we're going to do it. It's a little bit weird to come up with a what and then go back to the how later, which is kind of how we're doing it in this course. But that's also not an unusual way to do it. And then, of course, we know that different people will read the requirements documents. So customers might read them to make sure that all of their needs have been met and everything is delivered as they ordered it. Managers might read it to plan a bid for the system. Engineers, of course, will read it to understand what it is that they're actually supposed to do. And then test engineers, which are usually a different group of people than the regular engineers, will read the requirements to develop tests for the system. And of course, maintenance engineers, obvious reasons again, will read it to understand the system further. There are different templates that you can use out there. We've avoided those templates because they're usually for large systems. And generally speaking, the more incrementally delivered your project is, the less detail you will have. Our project is not really incrementally delivered, but you're going to have about the level of detail you would have if it was. We just don't have enough time to go into significant detail. So pretend this is an iterative process. Here's a template that you might have. You might have an overall summary and a preface, some kind of introduction describing overall how the thing works, the glossary. You do your user requirements in one section on their own in natural language, maybe some diagrams there too. And you could do a system architecture, but we're going to skip that and leave that to the design phase, so don't include that here. You might do your system requirements in their own section where you split the functional and the non-functional system requirements up. Then you might do a system model. Again, we'll probably leave that to our design phase. And then you might have a section on evolution or maintenance or what happens when the project's done. Some appendices with other helpful information, and then an index. Obviously, this is a very complex template. I wouldn't expect you to go this far into it. Let's talk a little bit about requirements validation, since this is an important part of the process. How do we demonstrate that the system actually defines what the customer really wants? If there is a problem in the requirements, as you will see from the case study that you have to finish by, I want to say, Thursday, check Canvas for that exactly. If there's a problem with the requirements, then those costs are usually very high. So we definitely want to validate that the customer is defining the system that they want. Fixing a requirements error after delivery might cost 100 times more than it costs to fix a simple implementation error, or more. 100 is obviously a number that they yanked out of the ether here. It could be 1,000 times more too. Finding out that you are missing or you have not implemented a requirement correctly can be very, very expensive indeed. So we're talking about validity. Does the system provide functions which best support the customer's needs? Consistency. Are there any conflicts in the requirements internally? Completeness. Are all the functions required by the customer included? Realism. Can the requirements be implemented giving the available budget and technology? This is one that you guys are going to have a lot of problems with, since none of your projects are really realistic as described by the customer. Verifiability. Can the requirements be checked? This is another important one I mentioned last time. You need to make sure that all your requirements, as much as possible, are verifiable, that we can go back and confirm objectively that you delivered them. So how might we validate requirements? Well, we might do systemic reviews, manual reviews. You might meet with the customer and review together. We might just create simple prototypes and then present those to the customer and the stakeholders and see if that prototype meets the idea of what was supposed to be done. We might generate test cases automatically or manually to develop tests that automatically check our requirements when possible as we continue to add to our program. So if we do decide to do reviews, then we would probably do those while the requirements are still being formulated, so it might not be a bad idea for you to conduct a review at this phase. They might be formal, they might be informal. You might want to talk to the customer or the users again to try to resolve those problems. Make sure that your requirements are what the customer actually ordered. Otherwise, obviously, your team will run into problems down the road. So check. Verifiable? Are they realistically testable? Are they comprehensible? Can we understand these? Can other people understand these? It might be as simple as asking an outside third party like you did last class if they get it. So you've got some feedback there. Apply the feedback that they gave you to make your document more comprehensible. Traceability, origin of the requirement clearly stated, and adaptability. Can we change a requirement without a large impact on another requirement? If it says 10 minutes and we make it 15, is that going to be a big deal? Probably not. If it says use Java and we switch to C++, that might be a big deal. So adaptability is a helpful thing. Not essential to every requirement, but nice to have occasionally. Of course, requirements change. The business and technical environment always changes, and the people who pay for the system and the users of the system are almost never the same people. Something to think about very hard. Let me repeat that. The people who pay for a system and the people who use it are almost never the same people. All right, so enterprise applications are ordered by management to be used by the rank and file, and even applications that are designed for end users, the people who are paying for it are the investors or the shareholders in the organization. They are rarely going to be the people who use it. Does Mark Zuckerberg use Facebook a lot? Probably not. Does Jeff Bezos use Amazon a lot? Probably not. They might, but they probably don't use it very much. And if they do use it, they don't use it more than your average end user. Most of the people who invested in those companies also probably don't use them. And that's going to be true of largely any product. The people paying for it are not the ones using it, and that creates a pretty hefty conflict just between the customer, who is the person paying for it, and the end user, who obviously the customer wants to do right by in most cases, because if they don't, then they're not going to recoup their investment, whatever that may be. This is especially true in public projects, obviously, as again in the case study you're going to read. The people paying for it are the taxpayers, and they are very rarely the people who are using it, and they are not at all the people who are actually contracting it, which is the government organization that actually writes out the contract. So then you have three different groups: the people paying for it, people contracting it out, and then of course the people using it. Large systems usually have a very diverse set of users. Many different kinds of people interact with them. So it's nice if you have an application that's targeted for a very narrow audience, because then you don't have all these different contradictions of priorities that might make your requirements difficult to structure. And I think that's all we're going to look at on requirements for now. We don't need to look at requirements management here. Let's move on to the different kinds of diagrams that you're going to make today. System modeling. So this is a part of the requirements phase and the design phase. These kinds of graphical diagrams, models that we're going to talk about are very common in software engineering. We're going to talk about a few different kinds of models: your context, your interaction, your structure, your behavior, and your model-driven engineering, which we won't go into too much. So context, of course, talking about where it is that your system fits into the broader world, into all the other different systems and people and things that interact with it. Interaction models referring more to how users and others will interact with your system. The use case diagram is one of those we just looked at. Structural models are going to lay out the structure of your system. So these might be things like state machines, or diagramming what the classes and objects are going to be like. These are more a part of the design phase, so we'll look at those later. And behavioral models, pretty straightforward, but we'll look at those later as well. So, system modeling. We want to develop abstract models of our system that are as simple to understand as possible. If you guessed that UML stood for Unified Modeling Language, then you are correct, and from here on out we will just refer to it as UML. UML is basically just a fancy way of saying a very standardized form of sort of graphical notation that has come to dominate the software engineering industry. So generally speaking, when people are creating diagrams of their software, they will just, out of force of habit, use one of the various UML templates out there, which is good because we have very few standards in software engineering, as you've probably seen so far with the lack of different templating and things. It's nice for us all to have at least a rough understanding of what different graphs should look like in the form of UML. So make sure that as you make your figures, you do your own research and make sure that they fit the industry standard for what other UML diagrams should look like. There are obviously many minor variations between different implementations of UML graphical notation, but again, you should try your best to meet the industry standard. These are all very standard diagrams that we're talking about. They have a very particular template usually used. We'll skip this slide because there's a lot of words there. Perspectives, we can skip to for now. All right, so a few of the different UML diagrams. We'll look at least the first 3 today, and then the next few in the design phase. But they're kind of interspersed in this slideshow, so I'll just cover them as we go. Activity diagrams show the activities involved in a process. Use case diagrams we already saw show interactions between a system and its environment. Sequence diagrams show interactions between actors and the system, and between different system components. So you can think of those as objects or classes, or however you want to structure your system. Class diagrams show object classes and the associations between them, so these come straight from object-oriented programming. You might want to start thinking about how to break different projects down into classes now, despite that coming in a couple weeks. Well, in a week. And state diagrams show how the system reacts to internal and external events, and how the state of the system changes as events occur. So graphical models, again, very helpful for discussion, for facilitating discussion. They don't have to be perfect. They don't have to be 100% complete or model the system 100% accurately. The role of these diagrams is to provide a rough idea. They are useful in documentation because they are much easier to understand than language. And as a detailed system specification, you may want to use graphical models as well. Of course, in that case, they do have to be correct and complete, which means that you have to put a considerable amount of effort into them. Something that we're probably not going to do in this class is try to generate a full, correct, and complete graphical model. So think of yours in a more informal way. Try to make them as correct and complete as possible, but don't think that you have to be Perfect. So let's look at the context models. These are probably the least well-defined in terms of templating. If you Google the different models that we talk about in class today, you'll see a number of different appearances for them. There are some standards, but there's quite a bit of variation. Some flow left to right, some flow top to bottom, some have differently shaped boxes, some use brackets, some don't. So it's a lot of differences in how these are structured. There are some things that are consistent between most versions, but these probably have the least standardized template. Context models are used to illustrate where a system lives in the broader context in the world, where it lives in the context of maybe the society it's in, the organization that it's in. Let's look at an example. We're trying to define system boundaries. We're trying to establish what the system covers and what the system does not cover. Where we put that boundary has a pretty profound impact on what it is that we're actually going to have to do in our requirements. So where our system ends and others begins is actually a very big decision in terms of how much work we're going to end up doing. Let's say that we interact with a payment processor. Where does our system stop and where does the payment processor system begin? Do we just talk to them and then they reply yes or no and we decide whether or not to approve a transaction? That would be great. If there's more work to do, that might be considerably more work to do. So defining a system boundary, sometimes that's a political judgment, sometimes it's a technical one. There are various reasons why you might want to cut the boundary of a system in a particular place. But context diagrams usually look quite simple at the end of the day. Here's an example for ment care. The system's usually positioned in the center. You have all the different external systems that it interacts with just coming off of it, and they're all named. Here they all use the tag system. Again, if you research these, look these up, you'll see there are different tags that people will use besides system. There are different formats for grouping the things together based on what type of thing that they are, like system or some other external requirement. Here we're mostly referring to softwares, so we've got our patient record system, our management reporting system, our admission system. So this ment care system that we've been talking about, it's going to interact with all of these. It's not going to tread into their territory, it just gets input and output from them. So the other systems are kind of like a black box as far as ment care is concerned. There is no code overlap necessarily. We're not going to develop into the other systems. We probably don't have to work with their code base or anything. So ment care ends basically where those systems begin, but we are going to be interacting with it. So a lot of you have projects where there will be external systems you interact with. Come up with a context document like this. Others of you will have a system that interacts with almost nothing, and your context diagram will be very, very straightforward. So it's up to you. It doesn't have to be that complicated. The more complicated one is the process perspective, the process model. Context models just show the other systems in the environment, not how the system is being developed or used in that environment. The process model shows us how the system is being used in the broader business sense, social sense, global sense, whatever. Let's look at how a process model looks. So let's say that the ment care system, which is again like a medical system that does drug stuff, I don't even really remember. Well, it's going to be involved when, let's say, a person is involuntarily detained for a medical reason. So we would follow that entire social process, or you could call it a business process, depending on how you think about it, of somebody being involuntarily detained. So one of the standards in this template is it usually begins with a circle and ends with an open circle. Again, sometimes these flow left to right, sometimes top to bottom. Usually decisions come in as these little diamond things you'll see. So usually the diamond will indicate that there's a conditional that needs to be met there. And then we have these what do you want to call them, vertical bars, I guess, or black bars to indicate when something either branches out or comes back together. Like there are different possibilities for how it proceeds. You can look again at other examples. This is one of the less standardized ones. But we see Mentcare fits into a couple places in this overall process. There are also other systems that fit into place in other places. Typically, the labels for where systems fit are put at the top and bottom. So this is a fine format where they're on the bottom only. So somebody is confirmed to be detained, and then they are informed of their rights, and we have to record their detention decision. That's where Mentcare comes in, recording that detention decision, and then we get to a choice. Either the person's dangerous or not dangerous. If they're not dangerous, they get admitted to the hospital straight away. The admission system will interact with them at that point. And then a few things will happen to them. Their social care will be informed, their next of kin will be informed, and their register will be updated. Mentcare will handle the registration updating process, which brings us to the end of the person being admitted for involuntary detention. And if they were dangerous, we would find a more secure place. If a more secure place was available, we transfer them to it. If it wasn't available, they'd go to the police station, and then regardless, they would end up still following those 3 steps. They would inform social care, inform next of kin, and update register. Notice this format is very clear about everything emanating from the vertical bars being executed either in parallel or considered the same step of the process, whereas the diamonds indicate a split where only one thing or the other thing happens. This format used a little shorthand here. Instead of putting another diamond for not available or available, they just split it off, so that's also acceptable in some templates. Up to you whether you want to do the diamond there or not. Well, actually, I guess research whether you should do the diamond or not. So those are context models. Now let's look at some interaction models. Modeling user interaction with our system. That's obviously very helpful. It helps us identify different user requirements. So we want to model system-to-system interaction, user-to-system interaction, use case diagrams, sequence diagrams. Let's look at some of these things. So use case diagrams we saw a little bit of an example of earlier. These are simple diagrams developed just to support requirement solicitation originally, but now they're used all over the place to generate user stories or just to trigger a broader discussion about whether you're covering all the different use cases completely. Each use case should be a simple, discrete task that involves an external interaction with the system. It could be as simple as user pushes the red button. It could be as hard as user attempts to sign in. It could be any of these things. Usually we just represent these in a simple diagram like that, where we have our person and then a thing that they try to do, and then sometimes, but not always, the person that it might affect. In this case, the patient record system is depicted as a person, which I found to be a strange choice. We might end up with a tabular requirement for that task that was just demonstrated. So that transferring of data in the requirements document itself might end up looking something like this. It might carry the same name, and then we have our more rigorous description of what that actually entails. Here's another example of use cases. So all the different things that the receptionist can do: register patients, unregister them, view info, transfer data, contact patients. Now, when you register and view patient info, you are also transferring data, right? So, one way to structure this, how you actually want to split these tasks and your idea of discrete might vary. Sequence diagrams are another part of UML, and sequence diagrams are often used after use case diagrams to add more detail to them. Again, the sequence diagram shows the sequence of interactions that take place. This one has a very standard template, so make sure that it looks the way all of them look. Objects and actors are listed along the top of the diagram, dotted lines drawn vertically from these. Let's just look at one. So all your different system components, you got the person, they get to be this vertical bar. Then the patient info portion of the system, however you define that, is this vertical bar. Sometimes they're color-coded, sometimes not. The database is a different bar, and then the authorization system is a different bar. So these vertical bars are all different system components or different objects. We usually like to think of these as objects because we're object-oriented programmers, but also, people can be their own bar, or groups or organizations can also be their own bar. Sequence diagrams always flow chronologically from the most old thing at the top to the most recent thing at the bottom. So the flow of time happens from top to bottom. This is actually kind of hard to do in practice sometimes. So look at a user attempts to authorize themselves. They send their info and their user ID to the authorization system, and then it responds with authorization. So a dashed line authorization here. And this is a response that happens obviously after the attempt to authorize. So chronologically it's further down because it happens after. So first you try to view some info. You ask the patient info system to view some info. The patient info system asks the Medcare database to generate a report. The Medcare database asks the authorization system if the user is authorized to obtain that report. You get an authorization back. If there is a branch, like something else can happen, it's like if the authorization fails, for example, we typically put that in a box like this. We try to avoid going more than one branch deep because then we have too many boxes, but sometimes you'll see boxes like this for a branch. And then we'll see either patient info gets sent back if the authorization was okay. Note they have like brackets here to designate this. And then the other alternative, which is split off on its own part in the box using a dotted line. If the authorization fails, then we get an error. We get no access. And then further down, there would probably be another line from the patient info back to the user that actually shows them what went on the screen. So you could go into quite a bit of detail here if you wanted to, or you could leave it high level, much like this one. And I encourage you to go find some other examples out there. There's definitely no shortage of sequence diagrams out there to look at. Here's another one. So medical receptionist wants to update patient info. Again, you've got your patient info, probably a database or something, your authorization system. Then you've got the, whatever this guy is, the patient record system, I guess. So first you log into the patient record system. Then you send some info to the info database. That sends it to the patient info database, authorizes with the authorizer, gets the authorization back. If it was okay, it does an update to the patient record system. Patient record system confirms that the update was okay. That sends a message back to the patient info system that that was okay, and so on and so forth. So one example of another sequence diagram for you. And I think that covers almost all of the possibilities you can make today. Structural models are more part of the design phase. I don't think we'll be using any of these, except there's one more behavioral one that you can use, I think. The activity model here, yes? Yeah, so this is kind of like another activity model that you might use. So this is different from a sequence diagram. It's similar, and we have the black bars and everything, and it's chronological. So actually, yeah, this is more like another format of sequence diagram than activity model. So yeah, I think that covers all the ones that you can use in yours today. And then also, don't forget, you also have to include one user story, which we mentioned last time, a user story or a scenario. So that covers it for today. I'll see you guys in Discord working on your UML diagrams, your user story, and etc. And we'll go through the rest of these slides when we get into our design document later. Okay, see you in Discord.